Hello everyone. In the previous session, we talked about sequence alignment, and now we know why it's necessary to know this method. And also, we talked about simple algorithms related to that. And today we are going to talk about dynamic programming as an approach in order to deal with sequence alignment. Now, we can see in dynamic programming, we have such an algorithm. Let's go through them one by one and try to understand them. Now, the first thing we introduce is the score of aligning A and B. So we got already introduced to this one, and we use it in our scoring metrics and scoring function, right? So this is pretty much the same. But now we have Fij, which we didn't talk about before. And this one we call optimal similarity of A. A means that your first sequence from the first element to the end, I, and B from the first position of the sequence to the end, which is J for the second sequence. So now we have a new factor here that we introduce. Now, what we will have is a matrix of I multiply j. So if you consider I as the number of row, we have j number of column. Now, how can we construct that table? Let me maybe show you one by one. Okay, for the first item, we have fi0, and we will have summation of the score of alignment ak. What is k? K varies from 0 to I. Why don't I have, for example, I1 to I? I will show you that's how we consider a gap inside this matrix. So this matrix in that case seems to have more number of row and column. So the first row and first column, I show them by gaps like this, right? So what I'm going to do is to align all the sequence of, for example, sequence 1, A, and second sequence B. So let me write, for example, sequence A here. For example, I have A, I have T, and so on. Here also, I may have another sequence B. For example, I have C, I have T, and so on. So for the first item that I have here as recurrence relation, I have Fi0. It means that I'm interested in the first row, sorry, ith row and 0th column. It means that I'm talking about this position. So I'm trying to fill these cells of my table. And I can calculate it by a summation of scoring of A, K, which means that it varies from 0 to I, and compare it with the dash. So here you can see A, B. It means that any elements from first sequence and second sequence, even considering the gaps inside them. So you see, we have gap here instead of letters. That's why we put in the formula gap, something like this. So what we are doing here, we are trying to fill the values inside my cells. For example, minus 16, minus 23, or something like that. We continue. And then in the second relation, we show for 0j. So again, I try to find the value of these cells and I continue until the end. So I deal with this first row as well. These ones, how we calculate them, I will show you, and also usually it's given to us by the assumption, but we can also calculate them as well. But the main part is related to this third relation. And this is very important for us, how we can find it. So for each one of these cells, we should calculate it ourselves by knowing the values of the first column and first row of this matrix. This is the formula that they use in dynamic programming. Whether this is the best formula or not, this is also one question. But of course, this is not necessarily the best. This is the best they have already came up with, and they are still trying to modify it. We have other algorithms which may work even better than dynamic programming. Dynamic programming is frequently used, and that's why we have it for our course as well. Okay, so assume that I want to find the value of F11. F11, it means that I'm interested in this cell. I want to find the value of this cell. So in order to find it, I need the information that I have regarding the other values in its neighborhood. So these three values. So if this position is 1, 1, let's see how the formula is related to the other cells. Like for example, this one. So if I'm interested to find F11, it means that here we have F1, J minus 1. What is J? 1. So 1 minus 1, 0. So in this formula, I should look at what is the value of F10. So the row is 1 because this position is 0, this one is 1, this one is 2 because we considered gaps. Here you see when we define Fij, here I can even start it from 0 instead of 1 because I've also considered gaps, okay? So even you can consider from 0 to I if you consider gaps. Otherwise, I 1 to I, as our sequence is. Anyway, now we should find what is F10. It's already given to us. So the first row and 0 column, we are talking about this one. So this is 0th column, 1, 2. We are talking about minus 23 here. So that's how we can find out about the values here, here, and here. The next thing we should know is related to our score of aligning A and B. When we talk about gaps inside them, it means that we are looking again for the first row and first column, and these ones are not inside this table. Be careful. The values of this score of aligning A and B is not inside this table. For example, in assignment 1, we already observed that how we should find the score of 2 alignments. That's related to that, not this table, okay? So we should apply the same rules like match, number of matches, number of, for example, penalties that we have for example, mismatches or gap. So that's related to that. This one sometimes is given to us, which makes our job much easier. And sometimes we should calculate it ourselves. We will see in the examples. And what is this one? This one is very similar to the first component that we introduced here. It means that score of, for example, matching A with A. Or, for example, score of matching A with T. Something like that. This is A, by the way. I don't know if you can recognize it. So a score of A with A or a score of A with T. And this one sometimes given to us. And sometimes we should calculate it ourselves, which is very complicated. So this is the whole idea of dynamic programming. In order to find Fij, and at the end of the table, we will finally find this Fij, the last row and last column, we have a cell. And this one, they call it sometimes the optimal answer. So there is debate that can we call it optimum, because this is just related to one letter in the first sequence and second sequence. So personally, I don't like to call it optimal solution for the table, but it can be useful anyway, because we can compare different tables together. And this number that you find here, it happened to be from all the numbers, all the values that you have calculated before. And that's why this number becomes important, and they call it the optimal answer for your table. But you will see that the other values in the table are important too. And sometimes even in the local alignment, you don't need to even consider this cell sometimes. And I will show you in different examples later. But in this slide, I just wanted to tackle each part of the formula so that you get idea about it. And later I will give you example. And even after example, as you could see for the first assignment, of course, I will give you assignments related to that. Then we practice together. We will have time for that. But another thing I want you guys to know about is related to dot plot. Dot plot is very important in sequence alignment, and it can give us ideas that what could be the possible alignment that we can consider. So let's see how it works. Let me activate it. Yeah. So for example, you have your first sequence here, second one here, and you just consider the whole sequence one by one, starting from left to right, and the second one from up to down. Whenever you have the same nucleotide or same amino acids in another table, for example, then you will put a dot for that one. So you see, T aligns with T, T aligns with another T. So for all of them, consider dots. Clearly, it's very easy to define it in our software, right? Whenever you have the same letter, then consider it one dot, and you can plot that graph. Okay, so what does it mean? For example, when you have all the dots together, when the sequences are too short, like these two, it will be very easy by just looking at it and get ideas that what are the possible alignments. But assume that you have a very long sequence, 1,000 nucleotides in one sequence. It's not easy to just look at the letters and guess what's going on. So when you have a plot like this, you may find about some trends. Let's see how we find trends inside these dots by just looking at these small sequences. Whenever you have the diagonal trend like this, for example, these three dots together, this is a diagonal trend, or this one. This is a good thing because it shows that if you have, for example, alignment of T with another T, it's a diagonal trend. It means that the next letter will be aligned to the next one. This is very good. It means that there are matches. And again, we have another one here. This one could be a good alignment, right? And these are just our guess. And it doesn't mean that we can find the optimal solution by just looking at the dot plot. But the thing is that in sequence alignment, we are trying to eliminate the possibilities which are not good for us as much as possible. And this dot plot can be very helpful. And you can find some trends by just looking at the dot plot and then try to eliminate the parts which are not interesting for us and find the possible alignments as much as possible. And what does it mean when you have vertical trend like this? It means that maybe it's better to just stop here at this letter and continue with the other sequence. How can we deal with that? With a gap. So it means that I will have T gap, and I will have T for the second sequence. That's how I can align them together. See? So this could be a good idea to have a gap, for example, here. Again, I can say the same for the horizontal case, like for example, this one. We have, for example, A for both of these A's. So it means that I can consider A dash for gap, and I align it with AA here. You see, that's how we can deal with alignments, and we can do it through the dot plots. But as I mentioned, there are just possibilities, but this is how to read from dot plots. So I already explained about the case of gaps, and can they be useful for aligning letters with gaps? Of course, they can be useful. We just mentioned. What if we consider gaps in the sequences of dot plot? So it will be a shape like the dynamic programming that we showed you, but clearly a gap with another gap, we call the score of that 0, and we don't even care about that. I will show you also in one example. So it's better to see them in examples to make sense. We have some frequent used score matrices for both DNA sequence and protein sequence. For example, these are the suggested values for that. For example, for matches, we can consider +1, for mismatch, -3. Now you already know about new gap or gap open penalty. I already sent you one announcement related to that to distinguish between different types of gaps. And these are just suggested values that you can use. They are most frequently used, but it doesn't mean that if they use it frequently, this is the best. Sometimes we should modify it. And in different examples, you may receive different ones. For protein, you can see there are even matrices which they have name. And for example, we introduced you PAM matrix. And for that, they have also different versions, and each version have different meanings. Maybe we will go through the details related to that later in examples. But you know, they have name because they are frequently used, and they have the same algorithm. That's the reason. And take a look at this one. Gap open penalty is -11 for protein sequence, but for example, DNA, we had -5 for that. For both of them, in the extension gap penalty, we have less value of penalty comparing to the new gap one, which is normal. I already explained to you why this is the case, because in nature, it rarely happens that you have several point mutations in the same DNA and they are separated. Usually we have, for example, one mutation which affect 3 nucleotides, for example, together. And that's why it's normal to consider gap extension penalty to be less than the new gap penalty. But why this one has such a high score as a penalty? And the reason is that when you have even just one amino acid difference in a sequence, that can totally change the structure of your protein. That's why we should consider big penalty for such a case. For any mutation, we shouldn't just let it go. But for DNA sequence, I already showed you one slide that we had a 1-point mutation, but at the end we reached the same amino acid, or even we reached one amino acid which had almost the same function than the other one. So that's the reason that you can see higher penalty for gap penalty in proteins. Take a look at this example. Again, we are trying to just play with it and see how we are doing sequence alignment. Again, this is not the best way. Just we try to tackle it as much as we can to see what bioinformaticians are doing in order to align their sequences. Let's say in this example, I see two sequences which have the same nucleotide from their beginning. This is also one approach to start everything from the left side, from the beginning. Should I consider one gap from the beginning, or should I just align the letter from the beginning? So what are the possibilities that I have if I have C as the first nucleotide for both of the sequences? I can align C with C, one possibility. And let's say based on the most frequent scoring function, I should give it +1. Mention it here, right? Frequent used score matrices. We are talking about DNA, so +1. Or I consider gap between, before the first nucleotide here and C itself in the second nucleotide. So I align gap with the letter. This is one possibility. I get -5. I opened a new gap. Again, for the next one, instead of here, I have a gap here. So the sequence starts from C, and we will have a gap here. Again, I receive -5. So these scores I just showed here is just related to the first nucleotide. Take a look at the remaining sequence. So forget about the first sequence. Either we consider a gap or a letter. This is the rest of the sequence. And you can see, for example, GA is aligned with GA here for the second one as well. For the third one, now we have 3 letters together. And maybe you would say this alignment would be the best because we align these two together and we receive +1, and also we align these two, and all together we align 3 letters together. But here in this case, this is true. Again, 3 alignments together. But the thing is that this codon would be important to synthesize a specific amino acid, which is very important for our proteins. So as we keep mentioning that it's not easy to simulate everything and to find the optimum answer just like that. It's complicated. But now we are getting introduced to different approaches that we can have, and dynamic programming is one of them, which we will give examples later as well. So another example, this one is related to sequence of proteins, or to be accurate, each one of them are amino acids, right? So for the first one, let's consider 2 nucleotides. Even we can consider gap after or before it. We could exactly mention the same method as the previous slide, but now we have different proteins at the beginning of each sequence. So in that case, one possibility is just to align P with H. Maybe they have similar function, right? So it's possible sometimes to have mismatches and align them together. Or one possibility is to consider a gap after P or before P. Never align one gap with another one, okay? Gap can be aligned with the letter, and that's it. So the scoring that we receive here is related again to the most frequent one that it was suggested. Again, it can be modified as mentioned before. So for the remaining sequence, again, you can see the same story. In this case, we have, again, 3 alignments. For all of them, this is the same. In this table, it's very clear that this one is the best option anyway, because you see, you reach exactly the same alignments here, no difference between them. But the score of the first amino acids, this one is much less than the other 2. So in this case, considering a mismatch alignment, could be much better than considering gaps. So you see, sometimes it's very obvious. We don't have any complicated case. Now let's take a look at this example, which is very important for us. Now we want to practice with dynamic programming here. Now assume that we have two sequences, and this score function is given to us. It means that whenever you want to align P with H, the score of that is -2. This is useful for us inside our formula. Let me show you here again. We had such formula for dynamic programming, right? So, gap penalty, not always this is exactly the same for all the gap penalties, but to make it simplified, then we can consider -5 for all of them. Now, assume that we are looking for this cell, M11, sorry. We don't have three-dimensional now. We have just pairwise sequence. So F11. This one is F00. This one is F10, and this one is F01. Now, by having these three neighbors of F11, it is easy to calculate this one. As soon as you calculate this one, it would be easy to calculate this because I have the neighbors, these three, or even this one, I have the neighbors. See? The one above it, the one on the left side, and the one which is in the diagonal trend. Whenever you have such a case, you can fill the next cell. You reach the final answer for Fij here. And as I said, sometimes it is important to compare different matrices by just this number here. Personally, I don't agree with that, just to take a look at it and judge the metrics just by looking at that. Anyway, I will show you also why I believe that. So how can I calculate F11 just as a practice? By using this law, I'm looking for maximum of 3 numbers. But how to come up with these 3 numbers? By using this formula. So if I'm looking for F11, consider I as 1, consider J as 1, and just insert it inside the table. So F10, F01, and F00. So these are the ones that you can see we can easily find from the table. And what about the score of these ones? Gap with B1, gap with A1. We consider penalty for all of them the same to be -5. So inside the formula, whenever you see score of a gap with the letter, we consider it -5. So you see, you can define even different gap penalties for different nucleotides or amino acids. This is interesting. In dynamic programming, we can do that. And for this one, what does it mean? Score of A1, B1. It means that inside your table, take a look at your sequences. Which one is A1, which one is B1? And this is P and H. We are comparing P and H. Assume that this one is A, this one is B. So we are comparing the first element of this matrix. Let's call it A, and this one B, which is PH. So we already given you this one. If you want to complete the whole table, then I need to give you score of each combinations of the letters, okay? So it means that by the assumptions that I've given you, you can only fill this one. But if I give you more scoring function values, then yes, you can complete the whole thing. For example, S, A, H, or S, W, H. You need to have them, otherwise you cannot come up with the rest of the values. So at the end, when you find about the values, these F values from the table S, which should be given to us, either it is a penalty or match or mismatch alignment, then we will find the maximum value, and -2 is finally the answer of this cell. So by having these neighbors and having the scoring values, then you can come up with each values of that function. Okay, guys, let's have a 5 minutes break, and we will continue with optimal alignment. If you have any questions, please ask me. I will come back about 5 minutes later, and I will answer them all.